Hello and welcome to eCHO. This is, I believe, episode number 34. So, as always, we'd love to hear from you, hear where you're watching us from. Do say hello in the comments. We've got a ton of news today. Let me just bring up the headlines. Got loads of articles to share this week. So I'm hoping some of you who've written some of these articles will be watching either live or at some point in the future. Do get in touch if you have other items, if you've written a blog post or made a video or in any way talked about Cilium or Ebpf. We'd love to hear about that. So what has been going on this week? We've got a bunch of talks. So let me just share my screen is there already. So the first of the talks that got broadcast this week is for Guild 42 in Bern. And Daniel Borkman gave a talk about Cilium and Ebpf and how it creates a really great data plane. And you will find on this site the slides and the video. Hi to Quentin, who is moderating for us today, and hello to Matthias from Berlin, Mattia, very similar names there, and Margarita, who's from Bavaria. Hi. Margarita is a previous guest. I can't remember how long ago, which episode that was, but good to see you again, Margarita. Okay, so do check out this data plane talk. And if you liked Daniel's presentation, you'll be really happy to see there's another one that he was involved in. This one here about BPF and Spectre, featuring Daniel, Piotr Krysiuk, and Benedikt Schlüter, talking about how we can use BPF to mitigate transient execution attacks like Spectre. I haven't seen this particular talk yet. I have flicked through the slides. It's really, really interesting stuff. And I have seen Daniel talk a bit about this. I think it was at Ebpf Summit as well. So it's fascinating stuff. And if you're interested in how that those kind of speculative execution attacks work, this is really eye-opening stuff. Hello to Asaduzman from Bangladesh. All the M's in chat. Yeah, in fact, we've got another M. We've got Michael from Bavaria as well. Hi to Christian from Peru. Great to see you with us. All right, and then there's another couple of talks, and I'm afraid they've got me in them. So here was one that myself and my colleague Christopher did for our friends at Container Solutions, and we talked about what Ebpf and Cilium are. They have a really fun series of WTFNRs over there. And I was also earlier this week on this Red Hat developer YouTube channel. It's called Cube by Example, KBE Insider. So if you don't get enough of me on today's show, you can check that out as well. Then if you've still not heard enough from me, I was on a podcast. Now, I actually recorded this last year, but it came out, I saw it a bit on the Twitter sphere this week, so I thought I'd include it today, where I had a really interesting and fun discussion with Guy from SNCC about security. Ebpf came into it. I enjoyed that conversation, so I hope you'll enjoy that one as well. And then another one I haven't listened to yet, but I hear is really interesting, with a past guest from eCHO, Dave Tucker, and Brent Salisbury, who were featured on this episode of Heavy Networking, talking about Ebpf and cloud native networking. So I can't wait to check that out. I hear it's good. So that's lots of things to watch, lots of things to listen to. We've got a few things for you to read as well. This is a really good article from Arthur Chow. I haven't worked through all the examples here, but it's exactly the kind of thing that I love. It's talking about how something works and showing you it in code. So what he's done here is implementing Kubernetes network policy and building an example of how that would work in Ebpf. So that seems like a really fun thing to check out. Then the other article that I've got for you today is about service mesh. I'm wondering if any of you watching today have tried out the Cilium service mesh beta. Say hello if you have. So we've had that beta out for, well, since just before the holidays, really. And we wanted to start hearing kind of how people have been getting on with that and starting to get some feedback on what the next steps should be. We've also shared in this blog some of the results that we've already seen around what features people are particularly interested in. And so, for example, you can see observability is outstanding as the feature that people really want to see from a service mesh. So we've got the results from that first survey here in this blog post, and you'll also see this link to another survey so we can get feedback for the next stage. Okay, that's some things to read, and then maybe there's some things that you might like to try out. There is an Ebpf debugger called EDB. I think this is very new, and it looks really interesting. I think the idea here is that you can run your eBPF code in user space to debug them more easily than you could if they were actually running within the kernel. So if anybody's tried that out, let us know. I think that could be a really interesting thing to explore on a future episode of eCHO. What do you think? Another new tool that we've seen is from Rancher. They've released something called LockC, which uses eBPF and the Linux security modules interface. So if you're a regular viewer, you might remember we had KP Singh on, I think it was in December, talking about how that LSM interface sits in the kernel and how we can use it to trigger eBPF programs to provide more flexible and bespoke security policies, but using that LSM interface. And this LockC project looks to be doing exactly that. So another really interesting development there. That would be fun to try out. And the last item I've got here under tools, it's not a new tool. It's a new location for the source code for BPF tool. So you will have seen we had Quentin on back last year talking about BPF tool and showing us all the amazing things we can do with BPF tool. He's got an incredible Twitter thread of, I don't know, 50 odd tweets with different items that you can use BPF tool for. If you want to build the code or look at the code, you can now find a copy of that on GitHub. So the main development is still going to go on the kernel mailing lists, but it's a much easier way to check out the source code for that. All right, yes, Matthias saying, let's bring up this comment, so much good content. I really do think it's been a busy week or two in the world of eBPF, which is fantastic to see. All right, so I think it's time to move on to the main topic for today's show. It's my pleasure to welcome to eCHO Frederic Branczyk. Hi, Frederic.
Hey, thanks for having me.
You're very welcome. So Frederic is the founder of Polar Signals, and they are working on a project called Parca. And yeah, we thought it would be really fun to have Frederic come on to eCHO and tell us a bit more about Parca, which is using eBPF, and maybe show us Parca in action. So maybe just give us a couple of sentences about what Parca is and why you've built it.
Yeah, of course. So Parca is a continuous profiling project, and continuous profiling is still kind of an emerging area in the observability world. So I think it's worth also spending a couple of sentences just on the methodology itself before diving into the tool itself. So continuous profiling is, in essence, just profiling all the time, right? Profiling has kind of been a part of the developer toolbox ever since programming has existed, right? Like I actually, when I started the company, I did some research, and basically since the 1960s, we've been doing profiling, because we always needed to understand what our running programs were doing.
And when we say profiling, we're talking about things like CPU usage, memory usage,
Correct.
that kind of thing.
Yeah, exactly. Theoretically, profiling can be anything where you have a stack trace and a number attached to that stack trace. So we've seen network I/O profilers. We've seen block device profilers. So really anything, any resource, usually you can associate. But sometimes there are even profilers that are specific to certain runtimes. For example, the Go runtime has a special profiler for understanding Go routines. Those are never going to be, let's say, in a generic profiler like Linux perf, because the operating system just doesn't know about concepts like that. So there are definitely also profilers that are useful for your specific language and runtime. But coming back to like continuous profiling, when we think about profiling, most of the time, the first thing that kind of pops into our head when we think about always doing this is like, this is like, that sounds expensive, right? Like profiling is kind of has this association with having overhead. And there are kind of, there's, I guess, two major reasons why we can do continuous profiling. So the first and foremost is that we use a technique of profiling called sampling profilers. So there are kind of a couple of different kind of profilers, and talking about all of them is maybe a bit too much for today. So I'm going to focus just on sampling profilers today. But sampling profilers are essentially that we look at a stack trace. In the case of CPU, let's talk about CPU. We look at a stack trace, let's say 100 times per second. And 100 times per second is actually relatively few for what a CPU does. And so that actually ends up having relatively low overhead. But because we're always profiling with continuous profiling, 100 samples per second over time actually accumulates, and we get a statistically significant representation of our program. And so that's why we can always do this. And then why we're here to talk about Evpf, right? Evpf kind of put sampling profilers on steroids in terms of overhead, lowering overhead, I guess, because we can capture exactly the data that we want in exactly the format that we want, and only export it every couple of seconds, as opposed to capturing every single sample. So
Right. Okay. So there's almost sampling at two levels. There's the sampling within the kernel itself from the Ebpf program, and then you can choose how frequently you export data from there into user space. Is that right?
Right. So it's even, so we use the like perf subsystem for this as well. But instead of doing what like the canonical perf tool does, which just captures a whole lot more data than what we actually need, we really only capture the stack trace and capture how often have we seen that stack trace, and that's it. And then every 10 seconds, our user space program kind of takes everything that we've saved in our Ebpf map, resets it, and after another 10 seconds, we iterate over it again. So really only every 10 seconds do we need to grab any data from kernel space at all.
Right. Okay. And when you were thinking about the idea for Parca, did you have we want to do continuous profiling first, or how can we do that? Or were you thinking, with this Ebpf thing, this is something we could do continuous profiling with? Was it Ebpf first or continuous profiling that you wanted to?
Yeah, it's funny that you ask it in that way, because when I started the company, my first reaction actually was, I don't want to concern myself with the collection of profiling data at all. I felt like the harder problem was storing it and analyzing it in a useful way. And I'm the last couple of years I've spent in the Go ecosystem, where profilers are excellent, like really high quality profilers in great formats, like in standardized formats. And so I felt like, at least for the start, that's a problem that I wanted to set aside. It wasn't until we kind of launched our like private beta program that we kind of realized that if we don't find a way to do, we called it generic profiling back then, where we wouldn't require a user to add instrumentation to their code, because that's how it works with Go, for example. You actually need to change your code, redeploy your code to start profiling. And that's something we wanted to avoid at all costs, to not kind of fall into the same kind of category of observability as metrics or logging or tracing even. Like tracing is the extreme, but even metrics and logging requires some amount of code changes and redeployment, right? So we were trying to find a way to mitigate this problem. And actually, since we've mentioned it a couple of times today, our very first proof of concept, we're actually just using Linux perf. And so after getting some like good successes with that, we were like, okay, how can we do something even better, or can we do something even better? And that's kind of how we ultimately stumbled into eBPF world.
Right. I think this is a probably relevant question from Christian about what languages can Parca support?
Yeah, that's a great question. So best supported are compiled languages today. So basically like Go, C++, C, Rust, Haskell, anything that compiles to machine executable code. There is kind of a middle ground that also works quite well, but doesn't quite work in the zero configuration way just yet. So whenever we deal with languages or runtimes that have a just-in-time compiler, they actually eventually do produce machine-readable, like executable code, right? So it takes a bit more effort, but most of those JIT runtimes usually write the kind of mapping of memory addresses to symbol data that we humans understand to some standardized place, and then we can grab them there. And that Parca does have support for as well. So like Node.js and Java, Erlang, all of these have support for this, but they do require you to pass a flag to your command. So it's not quite zero instrumentation, or it's not quite zero changes. It is zero instrumentation. You don't need to do anything to your code. But in the Node.js case, for example, I think it's like --perf map, I think, or something like that.
That you'd add to the node executable.
Yes, exactly.
Right.
However, that's really just an intermediate state. The whole purpose of the Parca project is that it's entirely hands-off. You only need to deploy the Parca agent, and you get whole system visibility. So that's just the perf map interface is something that the Linux kernel had standardized for perf, and so that's something that exists that we can already take advantage of, but we want that experience to be even simpler than that, right? As I said, it's supposed to be 100%. You don't have to do anything.
It's pretty interesting, I think, that if you have an interpreted language, your computer is going to be spending time doing the interpretation as well as actually doing the code. So I guess that's what you'll see in your profiling. Is that true?
So in the case where you have the JIT, we kind of see both, because it actually ends up being truly interpreted, machine executable code. But in cases where we don't have a JIT, like let's say Ruby or Python, it's exactly like you say. And those we also need specific integrations for, which we are working on, where we actually inspect the Python or Ruby runtime memory, because at the end of the day, they build kind of virtual processors. You can think of it as within the interpreter, And so we just need to read the frames that they built in their memory as opposed to on operating system stack. So it's all possible. It just needs more work. And unfortunately, for interpreted languages, it needs a per runtime specific support.
Yeah, that makes sense. Yeah. I feel like if you are prepared to do so, maybe we should see it in action.
Yeah, absolutely. Let's do it. So let me first share. It's fairly simple to set up. Let me actually share my.
While you're sorting out your screen, I'm just going to say hello to regular viewer Russell. Nice to see you. Hi to Dor and Vaishali. I hope I've said your names correctly. Great. And there is your screen.
So
showing. Excellent.
I've already got it set up because it's really just these 3 commands. What I'm going to show it on a Kubernetes cluster. And as I mentioned, we have kind of 2 components. We have the Parca server, which is the thing that stores the data and allows you to query the data with a built-in UI. And then the thing that actually does the collection and the actual profiling is the Parca agent. So they are distinct components. And so you can use these commands, for example, to set it up on a local Minikube. I happen to have Parca already set up. Let me switch to my terminal on a Kubernetes cluster. Actually, in this case, it is a K3s cluster, but it works just as well. Let's see. There we go. So I've got this set up already. So as we can see, as I mentioned before, we have the Parca agent running on every node in my Kubernetes cluster, and we have the main Parca server. And kind of topology-wise, I think it's fairly simple, actually. The Parca agent does the collection, as I said, every 10 seconds. It grabs the profiling data from every container running on that node, and then compiles that in the open standard Pprof, which is an open standard for representing profiling data that Google developed. And then the Parca agent takes that and sends that to the Parca server. And that's where we can then analyze it. And let me pull that up.
So it'll be the agent that is loading an Ebpf program, or I don't know if it's one or more than one, to do that profiling. Okay.
Exactly. We can actually, in a second, have a look at kind of, at least on a high level, how that works. If people are interested, we can jump into the Ebpf program itself as well. It's actually fairly simple. It's only, I don't know, maybe 80 lines of code or something today. But yeah. So when you kind of open the Parca UI, and this is the Parca server that serves the UI and then also serves an API to query this data. The first thing you would do is you would select the type of profile that you want to query. In this case, the Parca agent actually today only supports CPU profiling, but that's just a matter of starting with something, and CPU tends to be the most expensive resource that we have in terms of cloud resources. And that's why most people are most interested in optimizing their CPU time. So that's why we kind of started with this one. We definitely want to add, allocation profiling, network profiling, disk profiling, all of these things that eventually, contribute to not only the cost that occurs by using the cloud, right? But also being able to understand just performance characteristics of our running applications. So
yeah, my first thought was you'd use it for kind of optimizing performance and spotting bottlenecks. What is it that's causing something to take a long time to respond, for example?
Yeah, absolutely. That's kind of the classic use case for profiling, right? But we find since we have this whole system overview, we're profiling absolutely everything all the time, we actually get a really fantastic view of what is my biggest CPU offender in my entire infrastructure. And that then very quickly becomes a tool for cost optimizations, because we can actually statistically significantly optimize our infrastructure, right? Not like individual points in time. Those might be very interesting for, let's say, latency optimizations, but for cost optimizations, being able to see the whole picture and seeing statistically significant data is actually incredibly helpful. And as a matter of fact, it tends to be the #1 use case that we see for a tool like that, as opposed to performance profiling.
Interesting. We've got a question here that I think, since we're just talking about running on kind of managed cloud services, Dora is asking whether or not you've run Parca on a variety of different managed Kubernetes services. Do you think there's any problems running on those platforms? And I guess the question there is, can you load the Ebpf programs into the kernel on all those platforms?
Yeah, that's basically what it boils down to. That said, we have it, like our production infrastructure runs on GKE, so I can vouch for it definitely working there. We did make extra sure that it does work on the OpenShift container platform. We know of reports that EKS works and AKS, but I'm not sure about the Rancher Kubernetes engine, but as you said, basically all of this revolves around whether we can load the Ebpf program and whether we have access to the Kubernetes container runtime interface. And we do support Docker, we support CRI-O, and we support Containerd for kind of discovering the C groups to attach our profilers to for the individual containers. So that already kind of brings us to the topic that, if we have a CRI runtime that, let's say, is a virtual machine, that wouldn't work. I think there are like a handful of providers that do something like that.
I think maybe that leads me to asking, how does Parca discover the Kubernetes pods, the containers? How does it kind of know what pod is associated with any given stack trace, I guess?
Yeah, that's a great question. And this is also, I'll tell you how it is today, but also how it potentially will evolve in the future. So right now, today, the way that it works is we actually utilize the Prometheus Kubernetes service discovery. If you know me, this may not be super surprising because I happen to be the maintainer of the Kubernetes service discovery in Prometheus, and I'm generally a Prometheus maintainer. But essentially how it works is each Parca agent on every node basically asks the Kubernetes API to tell it what are the pods and containers running on the host that I am on. And whenever a new one gets created or deleted, we discover the C groups associated with those containers, and then attach our Ebpf programs using the perf subsystem to that C group. And that way, basically, every time, basically the perf subsystem is kind of buffer based. It's overflow based. So at most, we would get 100 samples per second, meaning like at most our Ebpf program will be called 100 times per second. That is configurable, but that's the default that we use. And so that's how we kind of get our sampling frequency, and that's how we can correlate a stack trace with a statistic time distribution. Because if we capture at most 100 samples per second, well, then one sample can be at least statistically looked at as 1/100th of a second.
And you've got an instance of that Ebpf program attached to each different C group. So I guess they're
Correct.
collecting their data kind of. Yeah. Hopefully we'll take a look at the code shortly.
Yeah.
Yeah.
Let's continue the demo here. So as I said, the very first thing you would do is you would select the type of profile. And as I said, this is all completely generic and based on the pprof format. So if you have pprof formatted profiles, let's say for memory, you can send those to Parca as well, and the Parca server will understand it. It's just that the Ebpf program doesn't support creating those today. So yeah, you can first kind of look at the cumulative metrics of each of the processes. And if there's one particular one, let's say we had a spike here, right? Maybe this one is one that we're particularly interested in understanding what's happening, right? And we can then browse this particular profile that was taken at that point in time and see where the CPU time was spent. So at this point, it's sometimes people haven't seen these types of visualizations yet. So this is what's called a flame graph, or actually in this representation, it's called an icicle graph. Funny association with our brand that was totally not intentional, polar signals in terms of icicles. I actually only found out after I had like created the company and the brand and everything that Brendan Gregg actually calls these icicle graphs when they're built from the top down as opposed from bottom up.
I think an icicle graph is a flame graph upside down, right?
Exactly.
Yeah.
Anyway, so the way you read these essentially is that the very top one, the root, kind of represents all CPU time of this profile. And then the further down we go, the spans are always relative to that root. So if we, let's say, hover over this one, we can see runtime.go exit, all the stacks under this particular function in cumulative make up 96% of our CPU time. And then if we go further down, it goes down. But basically what this means is that if there's a span, let's say, for example, this one, that has an overlap and not necessarily all children make up all the CPU time of that span, then that means this kind of gap in between here, that's optimization potential, because that's something that truly this function is doing, as opposed to what the children are doing here. Or if it's a leaf, if we can optimize this leaf, then it's going to have exactly that effect on the cumulative CPU time of our process. So that's just a quick intro into how to read these. And a couple of really cool things that you can do when you do continuous profiling, and this is not necessarily related to Ebpf, but I think it's important to understand why we're doing this on a high level. As I said earlier, what we can do is we can not only look at profiling data as a point in time, but we can look at all the CPU time our process has spent over the lifetime of this process, right? So here I've filtered down all of our data just to seeing the Parca container. So Parca profiling itself here is a bit meta, but what I want to demonstrate here is that we can look at the entire CPU time of the process's lifetime, and we can do that by hitting merge. And what it does is it truly took all the data that we just saw on that graph and put it into a single report. And why this is interesting and why this is good is now we've got not only a representation of this process at a point in time, but over the lifetime of the process. And if we can optimize something in this report, it means, because this is kind of statistically significant data, it means it will actually translate into a cost saving of our infrastructure. So that's why continuous profiling, or it's one of the reasons why continuous profiling is so interesting. And there are a couple of other things that are just possible because we're capturing this data over time. earlier we were looking at this peak, right? And so another thing that's really interesting to do is look at differences of certain points in time, or even entire versions of software, right? So it's kind of this question that's as old as software engineering, which is like, why was my process spending, like, having the CPU spike here but not here, right? And we can actually do that. We can select a point in time here, we can select a point in time here, and it will tell us, okay, in this case it was pretty dramatic, almost everything was worse, but we can see kind of shades of red where things were particularly bad, right? So here, this is the difference, as we can see in the second line in the hover bubble. It was plus infinity, which means that this entire span was not there at all in the first in the first profile that we selected. So looking at all of the spans here, basically what we can infer from that is garbage collection was happening at this point in time. And that's pretty typical to see in a garbage collected language like Go, but it's finally we have that true validation, right? Like, we're not guessing that it's garbage collection. We know this is the code that was executing. It was garbage collection for sure.
Right. Yeah.
And because the Parca project kind of works on all kinds of profiles, we can do this with memory. We can say, like, why was there a memory spike here? What was the difference? What was eating up all my memory? All of these kinds of things.
I think you've got at least one fan here, Madhav, saying this is so impressive. So awesome. Now, Michael, at least, and I'm going to vote for it as well, would like us to deep dive into the code. So is that okay? Can we do that?
Let's do it. Let's do it.
Great.
All right. Let me pull up. Let's see. I think it's going to be easier for me to navigate if I do it from my terminal. So let me share that. I think you can see my terminal again.
Do that, yes.
See, what do I have? Okay, that's fine. So the most interesting thing, I guess, that people are going to want to see is the Evpf program itself, right?
Yeah.
So got that. Whoops, it's not here anymore. Open the root. Yeah,
I see Parca agent.bpf.c. That looks good.
Yeah. So if you've done this kind sorry, I need to not use NeoVim. NeoVim doesn't like C code. I don't need a second. It freezes and then I can close it.
I am resisting saying anything about editors.
So just normal Vim will do it. So let's maybe take a step back before we dive into the program itself. The way that we build and kind of load our eBPF programs is using libbpf. I'm guessing that it's been discussed numerous times here, but just for folks to whom it might be kind of new. So libbpf kind of introduced, and I'm by far no expert, so if there's someone who's more knowledgeable and I'm saying something stupid, please correct me. But basically, it kind of started around this compile once, run everywhere initiative, because with like the BCC toolchain, the way that you did it was you shipped a compiler with the thing that you wanted to do something with eBPF with, and it would compile your eBPF program with the kernel headers on that particular host, not before you ship that program. And so we were fortunate to start this project late enough that the compile once run everywhere initiative was already like kind of very well established, and so this kind of turns the idea around where we can actually compile programs once to BPF bytecode, and then when it's loaded, things that are specific to this host are kind of, let's say, replaced on that host when the program is loaded. So there's kind of some relocations, and a couple of things are being replaced potentially, so that we don't actually have to have our like kernel headers installed anymore, and we can truly precompile our eBPF programs, let's say in our CI pipeline, and then load it on any compile once run everywhere like capable kernel. And that kind of brings us to one of the things that we like vaguely touched on earlier, which is this does require a relatively new kernel. So for newer things, it requires at least I believe it's 5.2 is the
right. And that
kernel.
relates to a question that Marcin asked earlier. He was wondering about Golang support, which isn't available on RHEL 8. I'm guessing actually it's more the kernel support that's relevant to whether or not you can run on RHEL 8.
Yeah, so actually kernel support works fine. Okay. We have a bunch of things in progress, and with some of those things that may not be the case anymore, because this ecosystem is moving so quickly that some of the things we may be using may not be supported in RHEL 8. I don't think actually Go 1.17 is necessarily supported. I think it's just what we happened to use when we did the like Go mod initialization. So I think that's something that we should check out. But we're doing our best to keep the kernel version as low as possible. But unfortunately, for like baseline compile once run everywhere, you need a 5.2 kernel. I'm not 100% sure which RHEL 8 kernel equivalent that is.
Yeah, fine.
So with that very, very long intro, that's how we write our eBPF programs, which is why you don't see, let's say, a string replacement in here or something. It's truly just the C code, and we compile it like that. So we, with libePF, this is also a little bit different with the BCC toolchain. We actually are even more restricted than what it was with BCC. So we need to pre-declare a bunch more things. So in this case, we say also how many addresses can be in a single. The max stack addresses are how many stacks can we unique stacks are we going to be able to capture, and then the stack depth is how deep are we allowing a stack to be that we're capturing. Then we've got a couple of Ebpf maps, and the interesting ones are which one was what one? I'm kind of reading this right now as well, but we've got one that has a mapping of a stack ID to the actual stack, right? And then we have another one that says the stack ID to the observations. So how often have we seen this particular stack? Because that's how we are going to ultimately infer the CPU time, right? Because we were saying at most we're doing 100 observations per second. And the way that we're doing that is by saying we've seen this stack with this ID, let's say 5 times, and that's how we're inferring the CPU time from there. That's essentially how any sampling profiler works.
Okay.
But because we're doing it like this and storing it in the BPF map, we can actually only every once in a while read these maps from user space, and all the other time we can just completely leave it running, right? Just whenever the perf subsystem decides this eBPF program should be run, it runs and inserts or increases this particular stack trace that we're seeing at that point in time. So these are the definitions. This one's also important. This was actually already used above. The way that we actually identify the stack that we're seeing with the counter is that we use the process ID, the ID of the user space stack, and the kernel stack. So that way we're kind of uniquely identifying the stack trace of a particular process.
Okay.
Here we're actually creating those, and then this is kind of a helper function. Let's skip over that for now. And here is
example. That looks good.
Yeah, this is the actual program. So the very first thing is we check, is this even a process that we are remotely interested in? I think 0 is that there's some kernel thing that's happening. So definitely not a user space program that we're interested in right now. And then we start building our stack key that we were defining above, right? And then we use a couple of BPF helper methods. So these are, we didn't write these, the BPF get stack ID. This is something that we get from the helpers. And here we're saying that we want the user stack. So what this does essentially is it walks the frame pointers. And we can talk about that in a bit more detail in a bit, because I actually we've got some kind of new things that we're working on in this area. So I've got some things that I can show about that, like some visualizations. But vaguely speaking, we can say that we're able to capture the user space stack and the kernel stack, which is on the next line here. And this essentially also, if this stack has been seen before, we kind of don't do anything. But if it hasn't been seen before, it writes it into our stack traces BPF map. And the way it basically works is that we have the memory addresses that make up the entire stack trace. That's the value of our BPF map here. And the ID is basically a hash of all of that. At least that's how we can think of it. And those are then what we use as part of our key here. Okay, and once we have essentially, at this point, we've built our stack, right? The key that uniquely identifies our stack. And at this point, we just kind of check if we've seen this kind of stack before. And if we haven't, we create it in our BPF map. And if we have, we just fetch it, and then we atomically increment it.
Yeah.
That's basically the whole program.
That's how we grab that stack information that's in the map. Your user space code is accessing that map. All right.
Yeah.
I guess another question, how did you, when you've got some Go code, obviously you're writing your eBPF code in C. Did you use an eBPF library?
Yeah, so we use Aquasex. I think you might have worked on that before, the libBPF Go.
Okay, yeah. Cool. All right. So we got a question earlier about whether or not you need to be root or even a privileged container to run the Parca agent.
Yeah, great question. So basically, whenever you want to load a BPF program and attach it to something, you're going to need to be root. Or I think, although it's not really any better, I think it's like capsys admin or something.
There's a cat BPF actually, but
yeah. But I think that one's really new, like 5.8 or something like that. But yeah, it doesn't really matter. You're very privileged once you're able to load and attach a BPF program.
Yeah, I think I often say, you shouldn't be giving out the ability to load BPF programs any more than you would give out root privileges, because you have the ability to change the way the kernel behaves. So it's great power but great responsibility.
100%. Yeah.
Yeah.
That said, we do put a great deal of care into making sure that giving us that privilege is, respected as much as we can possibly do that. And one of the things I think that is kind of cool, since I do already have my editor here, we put a lot of effort into actually doing byte-by-byte reproducible builds. So when you check out the repository and you check out, let's say, some of like any of our versions that we've released, and you build that container image, it will byte by byte be identical to the one that we've released. And so that way, we're introducing at least some amount of like supply chain security, because you can be sure that the thing that we've published is genuinely the thing that you're executing as root, right? So that and a couple of other things.
Not an easy task to build, reproducible builds in for Docker images is not trivial. So it's probably a whole other conversation we could have about that. But I think because we're getting fairly close to the end of the hour, and I know you have a few things to talk about around sort of what's coming next, and William has asked, he's hoping that in the near future there'll be things like memory disks and networking support. So do you want to tell us a bit about what the future holds for Parca and what you have in plan?
Yeah, absolutely. So there are a lot of things happening, and I'm going to keep it focused on what's hopefully most relevant to this audience. We have an entire company working on this kind of umbrella project, right? So there are a lot of things happening, but specifically in the BPF space, let me share some slides. Something that I'm really excited about, and I'm not actually the one working on this, but we're kind of collaborating on the idea of this. So as I said earlier, the way that we currently build the stack in the BPF program is using that helper. And the way that this helper does that is using something called frame pointers. You can think of it as when our operating system or our compiler really builds our stack frames of our compiled programs, it reserves one register to say where the upper frame essentially is located, or where it ends. I'm not exactly sure of the exact semantics, but it doesn't really matter. The point is that we can use the frame pointers to kind of walk a linked list to get the entire stack representation. And this is really great because walking a linked list is super fast. All of this is basically in L1 CPU cache. This is lightning fast. We don't have to worry at all about doing this in production. That said, unfortunately, and Brandon Gregg comments on this on his website as well. Unfortunately, there's a very evil compiler optimization that kind of ignores frame pointers and reuses that register that frame pointers are supposed to be written into as an additional register for performance reasons.
I didn't know that. That's crazy.
And this is incredibly common, unfortunately, in like the C++ world, but also when you do a Rust build and you do I forget if it's called production or release builds or something, the default is to omit frame pointers, unfortunately. And so if they're not there, that means that this strategy of walking up the stack as the linked list doesn't work anymore. So how do we still make this work, right? How do C++ programs still tell us, even if they omit frame pointers, how do they tell us when an exception happens, right? We still get what do they call it? Like an exception trace, I think. So how does that work, right? If we don't actually have that information, how to walk the stack? Well, there is an additional section in our ELF binaries that is kind of enforced to be there, called exception handling frames. And these basically, they're a lookup table, how you can compute where the frame starts and ends, and that way you can build up your frame essentially. But you actually need this information in order to look it up every time you're at some point in the stack, to then find the next kind of step in your stack trace. And so what we've been working on is kind of taking these exception handling tables and minimizing them to the absolute necessary information and passing them to our eBPF program. And that way we can do the walking even from within the kernel space, without needing anything else. Because the alternative, and this is what perf does today, is we kind of take an entire snapshot of the whole stack, put it into user space, and then unwind it from there, because we can kind of do that offline. But that has a couple of drawbacks. First and foremost, we need to kind of copy that stack every single time we capture a sample, as opposed to just walking a stack. But also it means that we're potentially grabbing some super sensitive data from a process's memory, right? And then at least somewhat persistently putting it into user space. And so ideally, we would be able to do this at collection time, right? And so I'm really excited about this, because it's kind of a novel thing. We haven't really seen this in other profilers before. So yeah, we're not even sure whether this is gonna work out, but if it does, it'll be pretty cool, I think.
Yeah, that is cool. Yeah. And a really interesting point that what is intended as an optimization could result in, if everybody wanted to profile their applications, they might have to find a way around that optimization. Maybe they could just turn off that optimization, but it's pretty cool that you'll have a sort of zero no need to change your configuration, no need to change your application approach to solving that problem. So that's cool.
Yeah. That said, please, if you have the possibility, please keep frame pointers. if like anyone who watches, if you're walking away with anything after this episode today, then please let it be, keep your frame pointers. It just makes life so hard. It makes debugging in production completely impossible. It makes capturing this kind of data impossible. And as a matter of fact, we've been speaking to several engineers who've built similar systems at, hyperscaler that you're thinking of right now. And all of the hyperscalers have essentially had internal conversations, and they all came to the conclusion it's not worth omitting them. Just keep frame pointers. The tiny performance gain that you're getting is not worth not being able to understand your systems.
Super interesting. I think that's a really great and interesting point to wind up on. I mean, we've almost hit the top of the hour. Unless there's any last points you'd like to make, Frederick.
That's it. Thank you for having me.
Oh, well, wonderful. Thank you so much to all our audience, and some great questions. Special shout out to Michael for encouraging us to dive into the code. I appreciate your help. And thank you so much, Frederick, for being with us.
My pleasure.
We'll be back, I think, next week. Duffy should be hosting in the US time slot. And thank you everyone for being with us. We'll see you again soon.